Good day, everyone. Welcome to 2023 IEEE Symposium on Industrial Electronics and Applications. Yours truly is Edgar Zapanta of Aaron Contracting Company from Kingdom of Saudi Arabia, a BS Electronics Engineering student of AMA University. My research advisor is Jeffrey T. Leonen of AMA University, Quezon City, Philippines. Today, we will be presenting to you our research work entitled Foundation Fieldbus Cascade Control in the Field Tuning using Particle Swarm Optimization. So this is our presentation outline consisting of introduction, methodology, the results of our simulations, and the conclusions. So let's get started. The problem statement of our research: there are numerous efforts in cascade control tuning that have been described in the literature to optimize and maximize the overall control loop performance. All of the cascade control tuning in the literature or in the studies conducted is basically in the conventional control system only. So no work has been published in the literature to show the control system tuning within a network-based control system such as Foundation Fieldbus network. A communication delay is the most common problem that affects the overall performance of the control systems. So the objective of this study is to employ particle swarm optimization to improve the overall control loop performance, especially the cascade control implemented in Foundation Fieldbus system, and specifically in the control in the field approach, in which the control algorithm is implemented in the field devices. So for our scope and the limitations, the particle swarm optimization approach will be developed in MATLAB to optimize the controller gain values of the cascade control systems for both inner and outer loops, or our primary and secondary control loops. So the obtained values will be subsequently used in Delta V distributed control system process kit simulator as our tuning parameters for cascade control loop, which is our level and flow cascade control applications. And the parameters or the tuning parameters obtained in the particle swarm optimization will be tested under step set point changes. And the performance of the control loop will be measured in terms of percent overshoot, percent undershoot, and settling time. So the importance of our study: this will remove the need for complex and time-consuming tuning processes for cascade control systems. Since cascade control systems involves two controllers, so the two controllers need to be tuned individually and sequentially. So normally, we tune first the secondary control loops, followed by the primary control loops. So in this case, it consumes more time in controller tunings. So secondly, the significance or the importance of our study: this will improve the control loop performance of the cascade control system, especially in Fieldbus network. So shown in this figure is a cascade control strategy implemented in Delta V distributed control systems under control in the field approach. Control in the field is basically the PID controller algorithm is implemented in the field devices. So shown in the figure, this PID controller is the primary PID controller implemented in our level transmitter. And the secondary controller is implemented in the flow control valve of final control element positioner. So in this approach, control in the field improves the overall performance of the control systems. Despite of these advantage, still there's a communication delays induced in the network. So our study will basically try to resolve the problem in communication delays induced in the network by tuning the controllers, both in primary and secondary controllers. So for our methodology, Figure 2 shows our process simulator skid, in which this is our simulators where we conducted our studies. So the field devices here are the differential pressure transmitter that measures the flow, the pressure transmitters to measure the level of the tank, the flow control valve positioner, in-with positioner, which controls the flow or the inlet flow of the tank. So all of these field devices are Foundation Fieldbus protocol. So this system is a single input and single output system only. Shown in this table number 1 is the parameters of our simulators, such as the tank height, cross-sectional area of the tank or the control tank, the capacitance of the control tank, and the volume of the control tank. So we have an inlet flow and outlet flow and the resistance of the level measurements. So using these parameters, we can model our system in the form of time constant as per the reference mentioned in this slide. So using the resistance and the capacitance value in table number 1, the transfer function and the system dynamics of the simulator is equal to the outlet flow over the inlet flow, which is equivalent to 1 over 1,200 S plus 1. It's shown in equation number 1. So 1,200 is obtained from this by multiplying the resistance and the capacitance of the tank. And the fitness function or the objective functions used in our particle swarm optimization is the integral absolute error shown in equation number 2. So this is the fitness function that will be used in the particle swarm optimization. The objective of the particle swarm optimization is to minimize this fitness function integral absolute error. In particle swarm optimization, as per this reference, involves 2 main mathematical equations. And these are the velocity modification equation, shown in equation number 3, and the position modification equation, shown in equation number 4. So this will be implemented in MATLAB to obtain an optimum values of controller gains for both primary and secondary control loops simultaneously. So shown in this figure number 3 is the particle swarm optimization algorithm. So starting from the parameters of the PSO or the particle swarm optimization, such as the population size, the number of maximum iterations, C1, C2, and weights. C1 and C2 represent the personal acceleration coefficient, and C2 is the social acceleration coefficients. After that, it will initialize the components of the controller, or such as the controller gains, the position, and the velocity, and it will begin the first iteration and weight updates. And after that, it will evaluate our fitness functions, the integral of absolute error. Then it will update the particles' positions and velocities. And then there will be checking of number of iterations. So if the algorithm did not reach the maximum number of iterations set in this process, the process will continue to update the best solutions and proceed to the next iterations and evaluate again the fitness function until the maximum iterations has been reached. And if the maximum iteration has been reached, then we can obtain the optimum values of controller gains for both primary and secondary control loops. So shown in table number 2 are the controller tuning parameters obtained from the PSO algorithm. So the KGP, KIP, and KDP represent the gain, the integral time, and the derivative time of the primary controller. So we have 0.4 gain, we have 10 seconds integral time, and no derivative time in the primary control loops. Same in secondary control loops that represent the KGS, KIS, and KDS for the gain, for the integral time, and the derivative time of the secondary controllers. So the gain of the secondary controller, which is our flow, by the way, is obtained with the value of 0.8 and 20 seconds integral time and no derivative time. In table 3 is the parameters or the tuning parameters from conventional methods such as the Ziegler-Nichols method of closed loop tuning. So we have obtained the value of gain, the integral time, the derivative time of the primary control loop, which is our level control loop, which is equivalent to 0.5 gain, integral time of 20, and the derivative time of 5 seconds. So the flow control loop or the secondary control loop using the Ziegler-Nichols closed loop tuning, the gain is equal to 0.3, the integral time is 30, and the derivative time is 7.5 seconds. So these are the tuning parameters obtained from our proposed algorithm, PSO algorithm versus the conventional method. So moving on to our simulation results. Our proposed method versus the conventional method have been tested into 5 test points or 5 steps, set point step change, starting from 75% to 25% level set point. So shown in left figure is the result of our proposed method using the particle swarm optimizations. And shown on the right is the results of conventional methods using the Ziegler-Nichols closed loop tunings. So as you can see from set point step change from 75 to 25% versus the response of the conventional method, as you can see in the conventional method, it reached up to the lowest or empty level because it reached 0, unlike in our proposed method, we did not reach the lowest level or empty condition of our control tank. And as you can see, the maximum or the percent overshoot is smaller compared to the conventional method. Same with the oscillate, the undershoot, and the settling time. Then we change the level set point or the level controller set point from 25% to 50%. So as you can see, same from the previous response, our proposed method is has a better control loop performance compared to the conventional method in terms of overshoot, undershoot, and settling time. Then we tested from 50 to 75% level set point of our level indicating controllers. So in this test point or step change, the proposed method still show a better control loop performance compared to the conventional method, such as the Ziegler-Nichols closed loop tuning. So from 75%, which we change back to 50%. Then, as you can see, our proposed method is still exhibiting a good control loop performance compared to conventional methods in terms of undershoot, overshoot, and settling time. Then finally, we tested from 50% to 50% level controller set points, and still the proposed method exhibits good control loop performance in terms of undershoot, overshoot, and settling time versus the conventional methods. So in this table of 4 and 5, this is the summary of our results of simulations. So we tabulated the graph readings or the trends of our level indicating controllers. So table 4 represents the conventional method using the Ziegler-Nichols closed loop tuning method, and table 5 represents the proposed method, which is using the particle swarm optimization method. So as you can see from the table number 4 versus the table number 5, which is our proposed method, the overshoot is much smaller compared to conventional method. Same with the undershoot. So the undershoot in conventional method is it reaches to a very low readings compared to our proposed methods. And finally, the settling time in conventional method is much longer than the settling time in our proposed methods. So from these results, we come up to these conclusions that the particle swarm optimization approach optimizes the controller's tuning setting for both primary and secondary control loops, resulting in good control loop performance in terms of percent overshoot, undershoot, percent overshoot, and process variable settling time. The PSO algorithm outperforms the conventional method Ziegler-Nichols closed loop tuning method in terms of computing speed for calculating the optimal controller tuning settings. Since this particle swarm optimization simultaneously tune the primary and the secondary control loop, unlike in Ziegler-Nichols methods, we need to tune individually the controllers. So that's why using the particle swarm optimization algorithms reduces the computing speed for calculating the optimal controller tuning parameters of the primary and the secondary control loops. These are the references of our studies, and thank you very much for listening.